Hey everyone, this is Dr. Walker. We're going to do our first example from v526, finding the electric potential due to a continuous charge distribution. Our first example is going to be finding the potential due to a uniformly charged ring. You should notice a lot of similarities between this example and when we found the electric field at a point P from a charged ring. But this problem is going to be a little bit earlier, mostly because we've just done this process so many times before. So this is a continuous charge distribution. We know that the potential at point P is going to be Ke and then the integral of dq over r. So the thing to realize about this is that the point P here is the same distance from every little dq, right? You can split this ring up into a whole bunch of dq's, and they're all the same distance r from point P. So this really simplifies the problem. First of all, we can write r in terms of the givens in the problem, which is the radius a and the distance x. Assuming that's the givens in the problem, we always want to write our answer in terms of the given variables. So we get Ke, the integral of dq over the square root of a squared plus x squared. And we know that a squared plus x squared is a constant, so it comes out of the integral. Ke over square root of a squared plus x squared. And now we have the integral of dq. When we solved this problem, when we're looking for electric field, what we did is to really get used to the steps, right? Is we figured out that, okay, we're going to want to write dq in terms of lambda dl, and then we said, okay, dl is going to be r, which in this case is a d phi, where we defined phi as an angle here, the angle subtending that arc, if I'm saying that word correctly, and then we integrated over phi from 0 to 2 pi, right? So the trick is we've always been writing dq into whatever variable that we want to integrate over. But if everything is constant, you really don't have to rewrite it this way, since none of this depends on any of the other variables that we wrote anyway. So the easiest thing to do, and you should go back to this problem that we did and see this, that once we get to this step, once we've taken out all the constants, then especially since it's a uniform charge distribution, lambda is constant, everything, then the easiest thing to do, and this might blow your mind, but that's okay, is just say, well, when we integrate over all of the charge, we just get Q, the total charge. And that's it. So if you go back to the problem that we did with electric field, you'll see that we could have skipped a few steps and gotten to that exact same result. But it's always good to really examine dq just to make sure that you are taking into account symmetry and all of that, which is why I showed it that way for the electric field. Alright, so we have found the field due to a charged ring at a point P located on the perpendicular central axis from the ring.